Right? So the purpose of thinking about it that way is I like to think that you try something, but when you say, "Oh, I'm trying this," you don't have the same intuition that, "Oh, I've been given this information, and now I have to believe temporarily that this information is true." Right? If the little bird tells you take this edge, then you can follow the edge and you can trust it. It also helps us focus on where are you going? I didn't tell you to do that. So it helps you focus on, now I know to take this edge, what's the hard question? What's the question I ask the friend? I need to give him a subinstance. So when you're coming up with a new algorithm for dynamic, a new algorithm for some problem, the hardest parts, intuition-wise, to come up with a new algorithm are this idea of what things do I try, and we express that as, what question do I ask the bird? And I think it's an easier way of thinking about it. And then the next thing that's hard is, if I have this information from the bird, now what question do I ask the friend? So those are the two parts that require creativity. And once you have those, then everything else kind of follows. The designing of the rest of the algorithm kind of follows mechanically, right? You have the recursive backtracking algorithm, which is you try each bird answer, and for each you recurse on your end, and then you combine your friend's answer with your bird's answer and take the best of the best, right? That's how you get a recursive backtracking algorithm. And then to get a dynamic programming algorithm, you then look at, you think about my instance, what is the entire set of subinstances that will ever arise from my instance, my friend's friends, and you build the table indexed by these subinstances, and you fill in the table in an order that nobody waits. Is everybody kind of getting that? Anybody confused about what I just said? So either you're lying to me or you'll all get perfect on the test. All right? What's wrong with this computer? I don't mean to be playing or anything, but are you? Should we it just died on us? I think you're right. You're right. That didn't look like computer. That looked like projector. All right.
Sorry, I just want to clarify about the weight table. What I don't get is that, and I don't ask this last time too, at the end you do another recurse over the whole graph again, right? From the example that we're doing to get the path.
How to get the path?
Yeah.
Well, the first time when you fill in the table, you fill in, for each subinstance, what you would like to fill in is the solution for that subinstance and the cost of the optimal solution. But the solution takes too much space to fill in and to copy around. So we just put the cost of the optimal solution and the bird's advice.
So we have bird advice for each instance, right?
Right.
So isn't that pretty much a path now?
Yeah, so exactly. So now once you have the bird advice for every subinstance, and for the case of graphs, you can think about the bird advice pointing to the parent, and you traverse the path back to S. But more generally, you can think about the recursive backtracking algorithm. When you have a bird, it's really easy, right? The bird tells you what edge to take, and then you recurse, and then your friend has a bird who tells him what edge to take, and he recurses, right? So you don't even need to recurse. You can just, okay, what would my bird say? And then you think about being your friend and what his bird say, and you follow it. It's really easy. So on exam situations, for example, as you all know, you're kind of limited by time. So I never ask you how to fill, how to do the part with the bird, once you have the bird's advice. I just assume that that's easy. I mean, you should think about it, but it is easy. Okay, come on, you can do it. Don't go away. When you're under pressure, you know. Now, I'm quite sure I remember what this password is.
This is why you like theory, right?
This is why I like theory. Exactly. Oh, there we go. And you know, part of the reason I have a hard time with is here, I got it down because I know the pattern. I remember patterns further than I remember numbers. So you have to go from that pattern to this pattern. Oh, it's the same password on the two machines. All right, what were we saying? We were coming over here. So now what we're going to do is we're going to look at other examples of problems. And before that, we'll simply focus on what kind of questions we'll ask the bird. So, questions for the bird. All right? All right, so this says, you know, the bird helps us focus on the difficult issues, as I said. It gives us a list of things to try. You temporarily trust the bird. It focuses on the remaining question for the sub-instance of the friend. Coming up with a question is the hard bit, right? So the idea is you think about the bird having a solution, and you ask the bird about some local bit about the sub-instance that the friend is holding, that the bird is holding. And you know, there are only so many questions you can ask, right? So let's give some examples. If the input is a graph and an ST and the solution is a path, then what is it that we ask the bird in this case? Did we ask about the first edge? Yes, but we turn it around. It's better to ask about the last edge, right? So ask about the first edge. But you know, as I said, dynamic programming turns everything around. So it's best to ask about the last edge. What is the last edge, right? So, and then what do we ask for the friend? We ask the friend for the rest of the path, right? And one thing that's nice about this question is that there's a nice follow-up question for your friend, right? Your friend can ask for the second edge, which is the first edge in the path he's looking for. All right? You only can ask the bird a little question. By what that means is that you need to be able to enumerate all the answers she gives, and you want there only to be a polynomial number of them, right? So, so you can think about the bird really only telling you the index of her answer, and we're going to iterate through those. So if you ask, for example, so here when you ask what is the last edge, how many answers can she give, right? It's the degree of this node. But on the other hand, if you ask what is the optimal solution, right, because you're lazy, well then, you know, there's an exponential number of solutions that she might give, right? And so that's no good. People kind of following that? You have to ask her a little question. All right, you could ask the bird how many edges are in the optimal path. Is that a good question? Why is it not a good question?
Of course, we don't know the optimal path.
Yeah, but we don't know the last edge to take. Right? So, what's wrong? Anybody think about what's wrong with it? Doesn't help us. How is that going to help us? Right? How does that help us? It doesn't help us. One, it's not a local property. Somehow it's a global property, right? And two, it doesn't help us solve our problem. How is that going to help us narrow down a question for our friend, right? And there's no real good follow-up question for your friend to ask, right? We already now know that, right? So, so here's another example. Suppose that the instance is something, I don't know what, and the solution is a sequence of objects, right? what's an obvious question to ask the bird? What's the first object? That's close. What's the last object? All right, we asked the bird, what is the last object in the sequence? All right, and now and how many different answers can she give? Well, it depends on how many last objects there might be. Right? If we ask our friend, now what do we ask the friend? Some instance such that the answer the friend gives is the rest of the solution. Right? So you have to think about, we want the friend to give this answer. What question do I ask? What sub-instance do I give the friend so that the friend gives me that? All right, so suppose that the instance is a sequence of objects. Right? Sequence means that it's different than a set because the order is there. Right? And the solution is a subset of these objects. Right? In fact, it's a subsequence because, you know, we put them in the same order. What's a good question to ask the bird? Right? Why don't we just ask the bird, what is the last object in your solution? Right? So we could ask what's the last object and how many answers would she give? Could she give? Right? It's kind of sort of the length of the number of things there, right? Does that make sense? Is there an easier question, a question that we could ask her in which she's going to have fewer answers?
You say what's the position of the last object?
That really boils down to the same, right? Because we have the string. But close. Give me something close to that. Last. Let's look at this A. Tell me something about this A. It's an A. It's a nice A, right? What?
It's not in the solution.
It's not in the solution. Yeah, I mean, I guess I should have said, ask some good question about that A. You know, we asked the bird, is the last object in our solution or not? Right? And so we can ask the bird, look at this last object. Do we keep it or do we throw it away?
The last A is different from the first A, right?
Yeah. Yeah, we want to be thinking about these A's as sort of as different because this is a subsequence. Right? It's not a loop, no. All right, so now how many answers can she give? She clearly gives yes or no. Right? So there's only two things to try, and that makes your algorithm faster. All right, suppose the instance is something, and the solution is a binary tree. Right? What should we ask the bird about? Should we say, tell me this leaf? No, what should we do instead? Tell me the root. Exactly. Right? So I asked the bird, what is the object of the root? And now what do I ask my friend? Well, you think, you know, it has to be a sub-instance, right? It has to be so he has to return, you know, if I'm looking for a tree, what's he looking for? He's looking for a tree, and is there a tree left? Right, we need two friends, right? I ask him what's the left subtree, and then I need a second friend to ask about the right subtree.
Could you just ask your friend, should I go left or right?
No, because I need the entire tree. Right, my goal, I'm looking for an optimal solution, and my solution is an entire tree.
But if he tells you to go left or right, then you can just take the left tree.
Yeah, but I want the entire tree. I'm trying to construct a tree. Right, so the game here is I'm going to, the bird will tell me the root, the left friend will tell me the left subtree, the right friend will tell me the right subtree. I will put all the pieces together. Right? Now this example differs from all the previous ones in that before, for every bird answer we have one friend. Right? And of course we have a lot of friends because we have a friend for each bird answer. But here we have, for each bird answer, for each possible root, we're going to have two friends. But that's okay, we can have lots of friends. Everybody kind of follow that? All right, if you'd asked about the leaf, right? It's a bad question because it doesn't make the problem that much smaller. It doesn't really, it's hard to come up with a follow-up question. I mean, what do you ask the friend? Give me everything but this root. It seems kind of odd, right? All right, everybody kind of get those examples? So just like we had, different types of loop invariants, here are different types of bird questions, and quite frankly, every dynamic programming algorithm that I can think of follows in those cases. So you're given a new problem, what do you think? You think about, I'm going to ask the bird one of those questions, and then you ask the follow-up question, and you're good to go.
For the edges themselves, can they have more than one piece of data and you're trying to find some combination of them? Like, it has like a length, but it also has like a cost and a reliability and speed. And
yeah, for sure.
You're trying to find the maximum reliability with the fastest speed.
For sure. And we're going to look at examples like that. And the problem with examples like that is they very quickly become NP complete. Right? You really don't have to ask anything too hard before there's no known algorithm for it. All right, so this is a problem that is in, Corman's, that big fat book. And this is one of the homework assignments in Corman. And I think my very first time teaching this course, it was a homework assignment. So I wrote up the answer, and that's why it's in the book, my book, and that's why we have slides about it. All right, so the problem is you have the input is a bunch of text that you want to print, and you have a number of columns on your page, and this is a very silly sentence, but as an example. But I first worked out the sentence knowing the number of letters in each word, and then it was hard to come up with the sentence. Actually, somebody later came up with a better sentence, which I think is in the book, but I haven't changed the slides. All right, so in your goal, a solution tells you what words to put on each line to make it as pretty as possible. All right, and what is the cost is somehow a measure of how pretty it is or neat it is. And what we're going to do is we want all the lines to be more or less the same length. So we count how many blanks are in the end of each line, right? And then we want to get one measure of how much we like this. Right? The obvious measure is you sum up these numbers, but that's pretty meaningless because if you switch the ordering here, it's not going to change the sum. Right? So what we do, any idea what we're going to do instead? Which number here do we not like? 6. We don't like the 6. So we want to say we really don't like the 6. How do we make the 6 uglier?
Uglier?
Yeah. Well, we want a big punishment here and a small punishment here. So how are we going to make a big punishment here? We're simply going to cube them all. All right? And the cubing makes this much bigger and says, hey, we really don't like big numbers. So we cube them all and take the sum, and that's what we're going to do.
What are you trying to do?
All right, the input is text. So for example, when LaTeX is one of the, I don't know if you've ever heard of LaTeX. You might write math papers in LaTeX, and what it does is it puts your text on your page in a neat kind of way. And of course, now everything does it. You type into Facebook or anything, and it decides where to break your lines. So somehow you have to decide. That program tries to break the lines so that it looks as straight on the end as possible. And so that's what our problem is you're given the text and you want to decide where to have line breaks. And what we're going to try to minimize, a solution is where to put the line breaks. And the cost of a solution is going to be you count the number of blanks on the end of each line and you cube them. And we run out of time. Oh, my knapsack. Boy, thank you. I'm going for the absent-minded professor field, especially today. All right, so then you sum them up, and that's what we're trying to minimize. Everybody got that? So, then we ask, well, how many ways are there to cut up the text? And and there's an exponential number of ways, right? Because you can keep saying, well, I put one word on or two words on each line. You can have a lot of different ways. So here, if we have this text here, here's one solution that has this cost. Here's another solution. It's a higher cost, I guess, because it has the 7 cubed that's killing us. Over here is another solution. It happens to have the exact same cost as that one. Right? So what we want to say now is, oops, you saw that probably. Given this solution, given this problem, you think about the bird having a solution, what question are we going to ask her? Right? Anybody? Did you see that answer come up?
How many in the last one?
What?
How many in the last one?
Yeah, we want to know something about, the solution is the sequence of things, and well, we already know what the words are, right? So really all we need to know is how many words do we put on the last line? Right, does that make sense? We just asked the bird, how many words do you put on the last line? And now, she's going to give us some answer, right? She's going to say, put 3 on the last line. I mean, she could have chosen, this is optimal too, she could have said, put 2 on the last line, but, she's going to say, put 3 on the last line. Right? And now what do we ask our friend?
Second.
Right? We have this instance. What instance do we give our friend? Yeah, we delete the last 3 words and we ask our friend to solve the rest of the problem. Right? So we ask the friend how to print the n minus 3 words. Right? Our friend gives us that answer and we combine. Right? He gives us this, and our solution will be the combination of the two.
The 11 is the number of letters.
It's the number of bits. Yeah, not bits, right. The number of characters in a line. And the reason it doesn't look straight here is because characters are different widths, and we're not getting into that bit. All right, we combine them to get our answer. All right. So, and if the bird is wrong, we haven't wasted our time, right? Because we learn here, this here is the best way to print the text, our answer, that's consistent with the bird answer that you put 3 on the last line. Right? And then we try each bird answer and we take the best of the best. Everybody got that? What's the running time of this? Well, I try all number of things on the last line, and then my friend tries, he recurses and he recurses, and so it's exponential.
Why do we cube all the previous?
Why do we cube them instead of squaring them or instead of doing something else? Yeah, I don't know. So latex cubes them, and I guess if you square them, well, you don't want to just take the sum because if I change the solution, it doesn't change the sum. Right? So somehow I want to make the bad numbers, the 6, worse. And one way to rank it worse is, squaring things make bigger things bigger, and cubing things make big things even bigger. And so it's how much you want to penalize the big numbers. And that's what latex does, and that's what the problem in the book was, and that's what we're doing. Does that make sense? All right, so you can see how if we trace this recursive tracking algorithm out, it would be exponential time. Right? Does that make sense? All right, so instead, we're going to, just as we did here, we want to determine the entire set of sub-instances, because every sub-instance we're going to allocate to one friend. So we think about, okay, here's my text, right? What are the instances that arise for my friends and their friends and their friends, right? So we run the recursive backtracking algorithm, we determine the entire set of sub-instances. So, for example, is that going to be a sub-instance that any friend is ever going to have to solve? Right? Sure. In fact, that's the one where you deleted the 3. Right? Sure. Right? How about that one? Is that one ever going to come up? No. How about that one? Is that one ever going to come up? No, because they all start with love. Right? Everything starts with love. All right? So You work it out, you can figure out it was just like what we did before. It's all the prefixes. Right? So the set of substances, right, so this is our guess. The guess is that it's the set of all prefixes, and now we make sure that it has the properties. Does it include our original instance? Yeah, it does at the top. Right? Is it closed under friend operation? It means, think about any subinstance in the set, right? Suppose that this is our subinstance. Who are his friends? His friends, you know, what his bird says, remove some of his last words, and so his friends are also in there. Does that make sense? And do we need each of these? I mean, do we have too many of these? No, you can imagine we need each of them. Why do we need him? Well, we need him because, and then the bird says one, 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 so we need him. Does that make sense? So we need them all. That's our set of subinstances. So now that we have our set of subinstances, we have to build a table. What's the table going to look like? Right, we need to think about each of them. Try indexing each of these guys with an integer, right? And what do you clearly index them with? Well, 0, 1, 2, 3, 4, the number of words there, right? It seems to be a good index. So, in what order do they go so nobody wins? Who goes first? Right, the small guys goes first. Smaller to the largest. The first is him, the last is us. Right, people following that? So we get our table, and so this entry in the table would probably be, you know, give me the best way of printing the first 1, 2, 3, 4 lines. Right? Does that make sense? All right, so this is, we're kind of filling out the table. Let's figure out what all these things is. Here's an instance. What does this mean? This means I have the text. I think we instance number 5 for the table. What is the instance? That's the instance. We have 11 spaces on the line. We have 5 words, 1, 2, 3, 4, 5. The first word has 4 letters, the second has 4 letters, the third has 3 letters, 5 letters, and 5 letters. Right? That's what we need to know for the instance. Right? What is a solution? A solution, the optimal solution for this turns out to be put 2 words on one line, put 2 words on one line, and put 1 word on one line. Right? So that's the optimal solution. What was, right there it is, the optimal solution. What's the bird's advice? The bird's advice was put 1 word on the last line. Right? And what's the cost of the solution? Well, don't worry about this math right now. If you worked out the cost of the solution, it would be this. Everybody kind of figure this table? We're filling this table out. So after we filled it out all the way up to, alright, so there's how the cost is. If you look at the number, right, it's 2 cubed plus 2 cubed plus 6 cubed happens to be 232. Right? So now, assume we've filled this table up to here, and now our goal is to fill out this last line. Right, so how we do it? We say, okay, this is my instance, and I need to think about how to make, you know, what the solution is. So I'm going to ask the bird how many words to put on the last line. My bird says 1. You know, I'm going to try them all. She says put 1 word on the last line. We trust her. So what do? We put 1 word on the last line. Right? There's our 1 word on the last line. And we ask our friend how to print the rest. Right? He has 7 words left to print. Our friend tells us how to do it. Right? And that gives us, and then we compute the cost of our solution, which is what? It's the cost of our friend solution was 16, right? Plus the cost of our last line is 9 cubed, right? Which gives us that our cost of this solution was going to be 745. Everybody follow that? Anybody confused? All right, so then that was great. We go to the second bird. The second bird says put 2 on the last line, so we trust her and we put 2 on the last line. And then we ask the friend for the solution for the rest. What does the friend say? The friend says, break them up 2, 2, 2, right? And he says that his solution was 43. So then we add on 6 cubes because there's 6 there, and we get that solution, right? And then we do 3. We put 3 on the last line. We ask the friend for the rest. The friend says do 2, 2, 1, and we combine his cost with the cost for our last line, and we get our cost, right? Then we go to 4. The bird says put 4 on the last line. And what do we say to the bird? We say, bird, we try to be polite to the bird. She's trying. We say, no, it doesn't fit. Right? So we say, the cost of that is infinity, and we kind of stop. Everybody get that?
The one on top says bird device is 1, 2, 2, 1.
Yeah?
So those are, why do we use them? When she gave us the bird device of 2, why do we use the last one? Like, when she gave us the bird device of 2, why did we say 2, 2, 2? Why didn't we say, like...
All right, so when she said 2, we come back here. She said 2, so then we put we be on the last line, right? And we take, then we ask this friend to put the first 6 left, right? And he says 2, 2, 2. So that's what we do, 2, 2, 2, 2. Right? And then we try all of these. And now what do? We take the best of the best. Right? We try them all, the best of the best. Now this is, you can see there are 2 possible answers which are best. And we can choose between them. And we fill in the one that we like. Right? And what do we fill in? We fill in what is our solution. We fill in the cost over here, I guess, and we fill in the bird's advice. Right? Everybody get this algorithm? So let's go through the code. Right? What are our subinstances? Well, we're given the length of all the words and the length of each line, and a solution. How to split the text into lines in an optimal way. What is the cost? It's the sum of the cubes of the number of spaces on the end of each line. What's our table? Well, so here you'll know I didn't do what I said you should do. 5 minutes, all right? What you should say here is we have a table, and index I is what's the best way of filling in the maximum number of words on, the best way of doing the text for the first I words. You should put in here what the text is, what the subproblem is, right? So then we loop through the instances. What is our current instance, right? So somewhat I'm doing the work that I talked about doing here, I'm doing here. I'm saying we're solving the instance this, which is, it's a sub-instance of that. We know what our instance is, right? So be clear what current instance you're working on. You can either say it kind of here, or you say it here, or you say it both, right? In fact, better to say it both, because then I'll make sure I catch it. Everybody get what we're trying to solve? We're given I words, and we know the length of each word, and we know the length of the line, and we need to know how to best split up the text, right? And then this calculates how many different word answers, how many different bird answers there can be. We want to know how many words can fit on the last line. So we flip through all the various bird answers, right? For be clear what the bird answer is. We get help from the friend somehow, right? The bird tells us how many words to put on the last line. So what's this here? This is the optimal solution given from our friend when you have I minus k words. And we're going to take his solution, plus we put the k words on the last line. People going to follow this? It's kind of cryptic, but it's there. And what's the cost? It's the cost of our friends plus we calculate how many spaces are on that last line and we cube it. Right? Does that make sense? Right, so here's the sevens that we give our friend. Here, we combine his answer to give our answer. We compute the cost. The base case is when you have no words, then you don't have to split up anything. And then you return the answer. People kind of follow that? The running time, as always, is the number of sub-instances times the number of bird answers. We have in sub-instances, we have less than in bird answers. Space is just the number of sub-instances, we're done. Alright? And then, to find, once you have the bird advice, it's easy to do the rest. Right? You just, this is here, the bird says 3, so we come up here. Right? The bird says 1, so we come up here. The bird says 2s, right? You just trace it backwards. People kind of follow that? And that's it. Right? And then that gives you, right? All right. Next time we're going to go back to, we're going to look at other problems. Any questions about, I'm going to be here until the last person's talking to me. If you want to talk about, oh actually she's coming back in, right? You can talk to me in the hall or you can talk to her, whatever you want. We're having a test on Monday. Good luck with it. We're, the usual pattern. Come here at 2:30 if you want. And I'll see you guys later.